for the class or just attending, please put in your name and the information required here. And I have to file this with Debbie later today. So please complete and circulate. So today we're going to keep on going with our discussion of hypersurfaces in space-time. And what I want to do today is to start talking about extrinsic curvature. So to characterize the embedding of a hypersurface in space-time in terms of the intrinsic geometry and the extrinsic geometry. And all of these are very important concepts that have a lot of ramifications in the theory. And I'll talk about some of these things later on as well. So today is all about intrinsic and extrinsic geometries of a hypersurface. And let me just mention the basic ideas first. So as usual, we're given a hypersurface in space-time. And well, last time we dealt with time-like, space-like, and null surfaces. And we sort of talked about all the subtleties associated with the null case, and we saw how to deal with them by introducing a generator-adapted coordinate system on each hypersurface. So, yeah?
What is supposed to put in ID?
If you have an ID number, you can put it in. If you don't,
So, this ID number?
Either the Waterloo or Guelph ID number. Yeah. So what I was going to say is that for the remainder of this section on hypersurfaces, for the remainder of chapter 3 in the book, I'm going to exclude the null case so that we can keep things a little bit more concrete and simpler. So everything that I'm going to do now will apply only to time-like or space-like hypersurfaces. And for this lecture today, I think I'll take concretely a case of a space-like surface, just again to keep things concrete. But the alterations you have to make to go from the time-like case to the space-like case, the other way, space-like to time-like, are very slight, so it really doesn't matter. It's just a matter of inserting a few epsilons here and there. So we have a hypersurface in space-time. In the space-time end of things, we have, whatever coordinate system we're using in space-time. And on the hypersurface, we have whatever coordinate system we choose to use on the hypersurface. So the hypersurface has its own coordinate system, which may or may not be simply related to the spacetime coordinate system. In the spacetime, in the bulk, we have, the coordinate system, we have a metric, G alpha beta, that gives rise to a connection that gives rise to a curvature. So all of this is very familiar, and of course all of this applies also to the hypersurface. As we saw in that coordinate system YA, we can set up a metric that's induced from the spacetime metric but applies to displacements on the hypersurface. From that metric, while we haven't talked about this, but we will talk about it today, from that metric we can also introduce a connection that's going to be compatible with that metric. So that's going to be defined in the usual way, the Christoffel symbols that will be defined purely in terms of HEB, which of course will have some relationship with the original Christoffel symbols, and we're going to work it out in the course of this lecture. And from this connection, we can also get a curvature tensor, and a curvature tensor that will describe purely the curvature, the intrinsic curvature of the hypersurface. And the central question I want to explore today is, what is the relationship between the spacetime curvature and the intrinsic curvature? And what we're going to see is that, the spacetime curvature is more than just the intrinsic curvature on the hypersurface. What we have to do to reproduce all of this is to combine that with the extrinsic curvature of the hypersurface. So basically what we can say, just to get started on this, is to say that the bulk curvature, or the spacetime curvature, evaluated on the hypersurface is going to be equal to the intrinsic curvature plus the extrinsic curvature. And what I want to do is to, of course, make this more precise and introduce those notions, precisely what is the extrinsic curvature of an embedded hypersurface in space-time. But all of these things here, I think I don't need to spend much time on. These are just the usual geometrical quantities that you get when you start with a 3-metric instead of starting from a 4-metric. So we know all about this. We know that this will characterize the geometry that observers restricted to the hypersurface will feel. But when we embed the surface in the bulk, we have more geometrical properties that arise because we know that we're being embedded in a 4-dimensional space-time, and it's that relationship that I want to work out. So in the book, I do all of this in covariant terms. So the point of view that I adopt in the book is to say, I don't want to know what the relationship is between the space-time coordinates and the intrinsic coordinates on the hypersurface. I know that there will be some relationship, but I don't want to work it out. I don't want to assume anything about this in the same way that I don't want to assume anything about that. And from that requirement, basically, I end up developing all of those ideas in purely covariant terms. And I think that's a valid approach. There's certainly nothing wrong with that. What I'll do in the lectures, though, is to do something a little bit different, where instead of keeping all the generality that I should with respect to the space-time coordinates, I'm going to tune the space-time coordinates very specifically to simplify all calculations. So sometimes you're allowed to do that. Sometimes it's desirable to play up the general covariance and make sure that everything is generally covariant throughout. But sometimes, it's better, or sometimes it's also appropriate to say, well, I might as well pick a coordinate system that simplifies my life because I have the freedom to do that. So that's the point of view that I'll adopt in this lecture and maybe continuing this afternoon, depending on how much time I want to spend on that. I need to spend on that. But basically, what I want to work out here, I want to explain what this means in precise terms. So what is that relationship between the bulk curvature and the intrinsic and extrinsic curvatures of the hypersurface? All right. So what I'm going to do, so here I'll be assuming that the hypersurface is space-like for concreteness. And that's just to keep things simple. And if it were, a time-like situation instead, by inserting various factors of epsilon, you would be able to, to relate the results that apply here to the results that would apply in a time-like case. So that's not a big deal, but we're excluding the null case. That's not part of the discussion here. To embed a null surface in space-time and to work out those relationships between intrinsic quantities and extrinsic quantities, you won't be surprised to hear, is quite a bit more subtle because already the intrinsic quantities are more subtle. We have this degeneracy of the metric and so on and so forth. So it can be done, but I won't do it here. Okay, so the first thing I'm going to do is to set up a very convenient coordinate system to work in the neighborhood of our hypersurface. And those are called Gaussian coordinates, Gaussian normal coordinates. And those will be the space-time coordinates that I will use in order to simplify my life. I pick a convenient coordinate system in the space-time, but I retain all the freedom that I want when I set up my grid on the hypersurface itself. So the coordinate system in the bulk will be fixed, but everything will be covariant with respect to changes in the intrinsic coordinates. I will retain that, and that's pretty important. Okay, let me introduce a little bit more notation before we get going. So I'll come back to this board. So I've already introduced these things. associated with the intrinsic connection, we will have a notion of intrinsic covariant derivative, right? And this I'll denote either with a D. For example, I might say that HBC is 0, and that's the statement that the connection is compatible with the intrinsic metric on the hypersurface, and that's the that's the notation for the intrinsic covariant derivative on the hypersurface. Or another way I might denote this, depending on what I want to do, I might denote it with a vertical stroke like this. So two notations for intrinsic covariant derivatives. And in the space-time, of course, we had our old notion of covariant derivative based on this connection, and that gave rise to a derivative operator that we used to call nabla, and that's the statement that the connection is compatible with the space-time metric. And of course, the other notation I use for this is the one with the semicolon. So vertical stroke, or D, for the intrinsic covariant derivative, and the usual notation for the bulk covariant derivative. All right. Okay, so to set up Gaussian normal coordinates around a hypersurface, well, you start with the hypersurface, so let's draw it again. So that's my hypersurface sigma. And the first thing I do is to set up my grid on sigma in any way that I want. So I set up my coordinate system completely arbitrarily. So these would be coordinate lines on my hypersurface. So here's one coordinate set of coordinate lines, here's the other one. So I set up my grid, and that's the arbitrariness in my YA coordinate system. The next step is I want to basically promote this into a space-time coordinate system. So I'm going to take this and basically propagate upwards and lower, downwards from the hypersurface. And the way we do it is to say, okay, well, let's pick a point over here that's going to be labeled by a certain set of coordinates YA. We have 3 of them. And what I'm going to do from that point is to launch a curve that's going to be orthogonal to the hypersurface at that point. So I launch my curve, and it goes up, and then, of course, it goes down as well, but I won't draw that portion of it. And that curve is orthogonal to the hypersurface, and I don't care whether it's a geodesic or not. I just, draw a curve like this, and I draw another one here with the same properties, and so on and so forth. So, so at each point on the hypersurface, I launch a curve that's going to be orthogonal to the hypersurface at that point. So we launch a curve orthogonal to sigma at each point, YA. And what we say next is to say that, okay, while that curve has a label that corresponds to the coordinate values at that point, I'm going to insist that as the curve moves up from the hypersurface, that it keeps its coordinate description. So the coordinates YA in the bulk spacetime are going to be designed so that they all agree, they all stay constant as I move up on the curve. So if this was the curve 1, 2, 3, y1 equals 1, y2 equals 2, and so on, then this will be at every point above the curve and below the curve, it's still going to be in the space-time coordinates. It's going to be the curve 1, 2, 3. And same thing over here. So this is the curve xa equals ya corresponding to the values here and the values there, and so on. So basically by doing that, I've promoted my spatial coordinate system on the hypersurface up and down from the hypersurface. And I'm doing this locally, so I don't want to go too far up, too far down, but I'm doing it in the neighborhood of the hypersurface. So the only thing I'm missing is a fourth coordinate system that's going to be measuring the distance away from the hypersurface. And for that, I'll just pick proper time on each curve. So we have t, so we have the spatial coordinates being constant on each curve, and then we have t proper time running upward on the curve and then, below the curve as well. So, lead point A. So each curve carries the label A, the label YA. And T is proper time on each curve with T equals 0 set at sigma. So we all launch the curves with T equals 0, and as we go up the curve, up from the hypersurface, T increases. As we go down, T decreases. So that's going to be our coordinate system. So the Gaussian normal coordinates are going to be x alpha, such that x naught is just T, and xa is just the constant labels on each curve that are inherited from the grid that we place on the hypersurface. So that turns out to be a very convenient coordinate system to use, at least locally, around the hypersurface when all your attention is really on the hypersurface. And that's why I'm picking that. That coordinate system, because of this construction, will give us a metric that's quite simple. The metric in space-time I'll just write it down and then I'll explain. It doesn't matter whether I use X or Y. It's clear if I use X in the bulk. So the metric has this property of being very simple. We have, a block diagonal. Well, it's not block. Well, yeah, it's block diagonal. So it has the feature of having a dt that's completely separated from the spatial increments, and it has the feature of having a -1 in front of dt squared. So all of this follows from the construction. So if we follow a displacement purely along time, so we set this equal to 0, we know that by going purely along time and keeping the spatial coordinates constant means that we're going along each one of those curves. And we know that t is proper time along those curves, so that's why ds squared ends up being equal to minus dt squared for those displacements. We don't have diagonal terms because of the fact that those curves are all orthogonal to the hypersurface. So the construction guarantees that we will not have cross terms between dt and the spatial displacements. And then if we have purely spatial displacements, well then if t is equal to 0, we're having displacements purely along the hypersurface, but we could consider displacements in the spatial directions at t, different from 0, so displacements above the hypersurface or below, in which case the metric would be whatever it is at those times. But when t is equal to 0, the space-time metric has to agree with the induced metric on the hypersurface. Again, that's guaranteed by the construction, because if I'm at t equals 0, if I'm on the hypersurface, then the coordinate system on the hypersurface agrees with the intrinsic coordinate system that we placed there at the start, and the metric therefore has to agree with the induced metric that we get in that coordinate system. All right. So the simplicity of the metric is basically why we use these coordinate systems. It really simplifies everything else along the way. If we're willing to live with this absence of general covariance, or if we are willing to fix the space-time coordinate systems, and for theoretical developments, that's usually not a bad thing to do. For applications, you don't want to necessarily do that, because in applications you would be given a space-time in whatever coordinate system. You would select a hypersurface in that space-time, and what you'll never find is a coincidence that would tell you that the original space-time coordinates you adopted would also be Gaussian normal coordinates for that hypersurface. I mean, when you're lucky, it happens. When things are very simple, it may happen But typically, you want to have something more robust than that. You want to retain the complete freedom of choosing those coordinates. So later down the road, I will give you, general covariant versions of what I'm deriving in this specific coordinate system. But to, I think, identify all those relationships that I mentioned before, I think this is a very good place to start. It really simplifies everything. And then, when you understand things in that coordinate system, you can promote everything to general coordinate systems very easily. And I'll tell you how to do that later on. So any questions about the construction or the properties? Yep. So basically T is proper time. So I declare T to be proper time for all the curves. And the only problem that the construction might encounter is that at some point those curves might start to cross. And if they start to cross, then I lose my coordinate system. So basically it becomes an ill-defined coordinate system. You end up with coordinate singularities. But so long as I work in the neighborhood of the hypersurface, those crossings won't occur. And I just declare that T is going to be, by definition, proper time along each curve. And that guarantees that this metric will be the metric of space-time in that coordinate system. Does that answer your question? Yeah. Another question?
Can this be used for four-dimension 2 surfaces?
Oh yeah. So that works. So here we're embedding, from 4 dimensions down to 3. We could do it from 3 to 2, and there's really no major differences. So it's really the same thing. Other questions? Okay. So let me move on from here. So basically what I want to do now is to calculate all sorts of space-time quantities in that coordinate system, and we'll see what we're getting. So for example, what I'll do is to use the specific properties of this coordinate system over here to calculate the Christoffel symbols in that coordinate system and the curvature tensor in that coordinate system. So there's a lot of detailed work that has to follow here. I won't do all of it. I'll skip the details. I'll give you the answers. And as usual, when I do that, you should take upon yourself, to go and check that in your own time during the lunch break, for example. It's a useful exercise to go through. But, it's just routine stuff that would take me a little bit too much time if I were to do that in detail in the lecture. So I'll just skip a lot of the intermediate steps and give you the answers. So we have a metric that has this neat sort of structure to it. So we have no off-diagonal terms in the sense of having mixed time and spatial components. The inverse metric also have a very simple structure. And GAB, this one over here will be the inverse to that one. So it's the three-dimensional inverse. And that's part of the inverse metric in the four-dimensional version. So when we do calculations, so we can plug that in. So for example, so just to make sure that the notation is clear, I'll call everything that comes from the four-dimensional bulk, I'll put a 4 on it. So the Christoffel symbols associated with the four-dimensional metric in that coordinate system, I'll donate it with a 4. And of course, that's going to be equal to the usual thing, where you take the space-time metric, you calculate all of its derivatives, package them in the right way, and just add them up like this. So basically what you do is that you identify all the possible components. So alpha can stand for T or a spatial index, beta can stand for T or spatial index, and gamma the same thing. So you just consider all the possibilities. You plug in what, for example, GT mu could stand for. If alpha is equal to T, mu has to also be equal to T because there's no mixed components. So you just work it all out like this systematically, with patience, because you have to make sure that you don't make mistakes in calculations like that. But if you do that, you'll end up with the following expressions for all the components of the Christoffel symbols. So I'll first set alpha equals to t, and then what I find is that if alpha is equal to t, there's no non-vanishing components unless beta and gamma are both spatial indices. And in that case, you find that those spatial components are given by the time derivative of the metric. If you set alpha equals to a spatial index, you find that one of them over here could be a t. So let's calculate this one. And in that case, you get half g a m, so that's going to be my dummy summation index, times the time derivative of the spatial metric. And when you look at all the spatial indices, you find that those are given in the usual way involving only the spatial components of the metric. So that's the result of the computation. That applies everywhere around the hypersurface in the neighborhood of the hypersurface. When I specialize this to the hypersurface itself, that is when I set t equal to 0, then I get something a little bit more specific. So the next step I'll take here is to just take that and apply it to t equals 0. So those are valid anywhere, and on sigma, that is at t equals 0, I get something a bit more specific, as I said. I get that the four-dimensional connection will have those components. This, I'll invent a new symbol for that. I'll call it KAB. KAB stands specifically for half the time derivative of the metric evaluated at t equals 0. This guy over here, on the hypersurface, the spatial metric will agree with the induced metric on the hypersurface. So in that case, I get HAM times half the time derivative of the metric, which is my KMB. And this is something I can express as KAB with the index raised. And finally, my spatial components of the space-time connection will all reduce to the three-dimensional induced connection compatible with the induced metric. So KAB turns out to be a very important quantity, and it has a name. So KAB is what we call the extrinsic curvature. And it's not obvious, but one of its properties is the fact that even though it's identified with the component of the connection, it's actually a 3 tensor. So if you were to look at how this quantity changes under a change of YA coordinates, you would find that typical components of the connection would change in a way that's non-tensorial, but this particular component would actually change as a tensor so long as all you're doing is to change the purely spatial part of the coordinates. So the claim is that even though this is not a tensor in general, those particular components behave as a tensor under a purely three-dimensional coordinate transformation. And therefore, KAB is a 3 tensor. And because it's a 3 tensor, it turns out to be a rather important object. And we'll see that it plays a very important role. And it plays this role that I described here as describing the extrinsic aspect of the curvature of our embedded surface. So you had a question first?
Isn't there a definition of plane where it says
Yeah, you can do that. Maybe I'll talk about it later. And I think in most textbooks you will find that K is defined as a 4-dimensional tensor. And to me, I find that less appealing as a point of view because it's really a tensor that belongs to the hypersurface. I'd much rather define it as a 3 tensor. But by using the tangent vectors, you can always promote 3 tensors to 4 tensors, and you can always pull back 4 tensors to 3 tensors. So in that sense, there's a one-to-one correspondence between 4 tensors and 3 tensors. But fundamentally, I would rather regard KAB as a scalar in space-time, but a tensor on the hypersurface. You had a question? Yeah, sorry.
So when you say 3 tensor, you mean a 3-dimensional tensor?
I mean a tensor defined as a tensor relative to coordinate transformations involving only the YA coordinates.
But it's a rank 0-2 tensor.
Yeah, so it's a it's a rank 2 tensor. So it's a let me spell it out more clearly. It's a 3-dimensional tensor.
So you mentioned it's a scalar in space-time?
Yep. I don't have my eraser.
There's one on that table.
Ah, thank you. So that thing is, let me say, a hypersurface tensor. By which I mean it transforms as such under YA goes to a new coordinate system. And as I said, it's also a collection of space-time scalars. That's not at all obvious from my discussion, because here I've committed to a very specific space-time coordinate system, and I don't have the freedom of checking whether or not this quantity is really a scalar with respect to space-time transformations. But if you follow the covariant route that I follow in the book, you'll see that this is a 3 tensor in the sense of the hypersurface, but it's also a 4-time scalar in the same way that the induced metric, that's something we talked about before. The induced metric is a 3-dimensional tensor. It's a tensor on the hypersurface, but it's a collection of scalars relative to space-time coordinate transformation. Okay. Other questions? Okay. So those are pretty simple things to calculate, and you should just go ahead and check this when you have a minute. And that allows us to introduce KAB as something interesting and important, and we'll see that it plays an important role in what we're going to be doing next. Something to notice, there are a couple of properties that are worth noticing. Of all the space-time connection components, the ones that have a T in it only have 1 T in it, so you don't have components of the connection that would have 2 T's. So you don't have a gamma T or a gamma A TT or anything like that. All of those vanish. So if you have a T over here, it has to be, there has to be only one of them. And then, of course, you have those that only have spatial components. The other thing to notice is that this KAB quantity is obviously symmetric. So it's symmetric because the connection itself is symmetric, or you can see it right here because the metric itself is symmetric. So it's a symmetric tensor on the hypersurface. Okay. To go from the connection to the Riemann tensor is, again, just a simple exercise. And it's actually not hard at all. You just have to plow through it. And again, I'll ask you to do that on your own time. But if I calculate the Riemann tensor on the hypersurface, on sigma at t equals 0, I get the following components. So here I keep all the indices down. So the 4-dimensional Riemann tensor will have the following non-vanishing components. If I pick this index to be t, then it's obvious that the second index cannot be t, because by the antisymmetry of the Riemann tensor, those components would vanish. I can slot a t in here, but then if I pick t here, I cannot pick that to be t for the same reason. So, so basically that's saying that you have components of the Riemann tensor that have two t's in it, and they have to be placed in this position, or, you know, or the ones you get from this by flipping and using the symmetry properties. So this one is equal to this. It's going to be equal to the second time derivative of the metric evaluated at t equals 0, because that's where I'm evaluating the Riemann tensor. And then there will be a term involving the square of my KAB quantity. So when you compute Riemann, obviously, you take derivatives of the Christoffel symbols, and then you have a bunch of gamma-gamma type terms. So these come from taking extra derivatives of our Christoffel symbols from up here, and these obviously come from the gamma-gamma terms. So you end up multiplying this times that, for example, and that gives you a KK type term. We have components of the Riemann tensor that have only one t in them, and these involve derivatives of the extrinsic curvature. And in fact, all of this can be packaged in terms of intrinsic covariant derivatives of my extrinsic curvature. So if this is a tensor, as I claim, these also are tensors. So this is a purely tensorial quantity on the hypersurface. This, well, it's not clear whether it's a tensor or not on the hypersurface because of that second time derivative. But this clearly is a tensor on the hypersurface. And then we have the purely spatial components of the Riemann tensor. So this is the four-dimensional Riemann tensor evaluated on the hypersurface, and it's going to be expressed in terms of the intrinsic Riemann tensor of the hypersurface, but there's more to it. And what's missing are terms in K that are quadratic in K. So that's the outcome of the calculation. The last two equations over here are interesting because they are tensorial. And they're sort of interesting to look at. And they actually have a name. They're called the Gauss-Cadazzi equations. Gauss, of course, is famous for having developed the differential geometry of two surfaces embedded in three-dimensional space, and all of those relations, you know, in a more restricted context, were, you know, came from him essentially, and I suppose he was a colleague or somebody who picked up his work after that. I don't know the history here, but those are the important equations. This one up here is still interesting. It's still interesting to look at. But it's not tensorial, and it doesn't quite play the same role as the other two. So interesting things to notice. The K is basically the time derivative of a metric on the hypersurface. And what we do here is to take spatial derivatives of that. So here we have mixed spatial and time derivatives of the metric, but it's only one time derivative. So these two relationships involve only one time derivative of the metric. These guys involve two time derivatives of the metric. So I'm just pointing this out right now, but I'll come back to that property when we talk about the distinction between initial value, the initial value problem in GR versus the problem of evolving initial values forward in time. The difference between first derivatives and second derivatives will be very important in that context. The other remarkable thing here is that, well, basically, this is the answer to the question I was posing before. What is the relationship between the bulk curvature and the intrinsic curvature of the hypersurface? Well, that's a big part of the answer right here. So the spatial components of the bulk curvature evaluated on the hypersurface are related to the intrinsic curvature on the hypersurface plus the extra stuff. So this is really the bulk curvature, at least the spatial components of it. This is the intrinsic curvature. And that, both of these guys, is, well, is what represents the extrinsic part of the information. So we call K the extrinsic curvature, but what is really meant by that is that it's this quantity quadratic in K that represents the breakdown of the full curvature in terms of an intrinsic part, and the rest of it, which is the extrinsic part. So this represents the intrinsic geometry of the hypersurface, whether it has its own curvature that you would perceive if you were purely living on the hypersurface. That is the extra curvature that you may get if the surface is bent in the bulk spacetime. So if there's additional curvature that's not captured by the intrinsic curvature, it's going to be captured by these terms over here, and these terms really represent the bending of the hypersurface in the enveloping spacetime. I'll look at examples of this so that we can be more clear about this breakdown. Question?
So these equations are true in not just in Gaussian normal coordinates, but unique coordinates.
These relations for now are true only in Gaussian coordinates. But the next step for me is going to look at, well, how do we make this covariant? And that's going to be a very easy step. You'll see how it's done in just a second. Yep. These guys are covariant. On the right-hand side, we have covariance with respect to three-dimensional coordinate transformations. On the left-hand side, we have components of a four tensor in a very specific coordinate system, the Gaussian coordinate system. So these guys are not covariant. So these are mixed equations. We have so we have covariance with respect to purely three-dimensional coordinate transformations. We don't have covariance with respect to four-dimensional coordinate transformation. It's in that sense. All right.
Since it's equal to covariant.
Again, it's covariant in the three-dimensional sense, not in the four-dimensional sense. So what I want to do is to turn this into covariant equations in the four-dimensional sense. Okay. Yeah. Yeah. I should always try to specify what I mean, because things mean different things depending on whether you mean three dimension or four dimensions in this case. Okay. We have the Riemann tensor. I'll come back to that in a second to turn this into a covariant set of equations. But since we have the Riemann tensor, we could go all the way and calculate the Ricci tensor from that. And from that, we could calculate the Einstein tensor. So let me do that and list the answers. And that will be interesting to look at because that's going to be a part of the Einstein field equations. So again, I'll be skipping a lot of steps, but the Einstein tensor on sigma, again at t equals 0, will be given by the following expression. So ironically, the Riemann tensor is very simple to write down. By the time you're done contracting and taking the Ricci tensor and then the Ricci scalar and packaging that into the Einstein tensor, you end up with rather large expressions. So I'll just write it down, and that's just what it is. So the TT component of the Einstein tensor is equal to the three-dimensional Ricci scalar on the hypersurface. That's what R stands for. And maybe just to make it very clear, I'll put a 3 here just so that there's no confusion. Minus two terms that are quadratic in K. And K stands for the trace of the extrinsic curvature, which stands for just the contraction of the metric with the extrinsic curvature. So that's the expression for the TT component of the Einstein tensor, so that's not too bad to look at. The mixed time and space component of the Einstein tensor involve the covariant derivatives of our extrinsic curvature. And the bad one is the purely spatial part of AB. Of the Einstein tensor, and that's a bit of a mess. So it's equal to the three-dimensional version plus all the rest of it, which is a mess. So let me just write it in full. So we have two time derivatives of our metric tensor evaluated at t equals 0. So clearly that's inherited from the first set of components of the Einstein tensor. Then we get a half HAB HCD times, again, two derivatives of the metric tensor. Then we have 2K AC KCB. Then we have a few more terms, 3/2 HAB KCD KCD. Plus K, KAB, minus half HAB, K squared. Yes, thank you. Okay. So the last one is a bit of a mess, but the other ones are not too bad. And what we recognize here is, so basically all the ingredients that were there initially in the Riemann tensor, they're just here with, in contracted form, packaged a little bit differently. So when I take all the contractions, for example, this guy, after all the contractions, will give me the three-dimensional Ricci scalar that appears here. And all those quadratic terms will appear in this way there. So that's a nice breakdown of the, bulk Einstein tensor in terms of purely, in terms of intrinsic and extrinsic quantities. These guys obviously will originate from these components of the Riemann tensor. So by the time you're done contracting and repackaging, you've contracted some of those indices and you end up with this expression right here. And this guy is the messy one that involves pretty much everything together. So we have, again, intrinsic things. We have extrinsic things appearing. And on top of that, well, we have those two derivatives of the metric with respect to time that appear here as well. And that breakdown turns out to be very interesting. And that's going to be my starting point in a few minutes when I talk about the initial value problem of GR. All the essential information is contained in here. Okay, so no more questions about this? Yep.
What's the expression for that cat to be derivative?
Oh, it's the usual thing, right? So if you take the covariant derivative of a purely intrinsic tensor or vector on the hypersurface, it's going to be the partial derivative minus the usual Christoffel terms. But the Christoffel terms are derived entirely from the induced metric, right? It's just the usual thing, but it relates purely to the intrinsic part of the metric. Other questions? Okay. So there's a lot going on here. And what I would like to do is to consolidate some of that and tell you, as I was telling you a little bit before, that I want to turn this into covariant expressions. So so just to repeat what I had before, all of those relationships here are applicable to the coordinate construction that we gave ourselves. So all of this is based on the Gaussian normal coordinates. I have complete freedom in setting whatever grid I want on the hypersurface. So we have general covariance with respect to three-dimensional coordinate transformations. But we've lost complete control over we've lost the freedom to change the space-time coordinates because we've selected the space-time coordinates very specifically here to basically respect the choice that we made on the hypersurface. So we have general covariance with respect to three-dimensional coordinate transformations here, but we don't have it with respect to the freedom to change the space-time coordinates. So in terms of working out the relationships, that's useful because that really simplifies the calculations. If you go through those calculations, as I hope you will in your own time, you'll find that this is very straightforward, very easy. If you follow the covariant route, you'll get there, but it takes longer. The steps are a little bit harder. And that often happens. Sometimes, to devise a good coordinate system to do some work and then bootstrap your way up after that to covariant expressions might be much more efficient than to follow a covariant approach throughout. And sometimes it's useful to do that. Sometimes, it's not particularly useful, so you might as well pursue the covariant route, and never deviate from that. But here's was a case where, it was actually convenient to deviate away from a covariant approach to get to the results more efficiently. But once you're there, well, the next question is, well, can you, in fact, bootstrap your way back to a fully covariant set of expressions? And it turns out it's rather easy to do that. At least in this case, it's very straightforward to do that. One thing I would like to do, and that's going to be the starting point of that, is going to be to go back to the extrinsic curvature. The definition we had clearly was very tied, where was it, to a specific coordinate system. It was over here. So the definition of the extrinsic curvature that I had before was very much tied to my choice of coordinates in the space-time. So what I would like to do is to consider a better definition that would be generally covariant. And this will be the starting point, and then we'll be able to do something similar for all the other quantities that appear here, including all of those components right here. So how do we do that? Well, what we're going to need is our usual basis vectors that we haven't talked about here, but the basis vectors that would come from the description of the hypersurface. So if I reintroduce those basis vectors, and by that I mean the tangential vectors that will live on the hypersurface and the normal vector that points away from the hypersurface, if we introduce those guys, then we'll have the tools we need to build all of this into a covariant set of expressions. So to turn all this into expressions covariant under a four-dimensional coordinate transformation, all we have to do is to reintroduce the vectorial basis on the hypersurface, and the vectorial basis was basically the normal vector n alpha, and the tangent vectors E alpha, which you remember are defined as the partial derivatives of the spacetime coordinates with respect to the intrinsic coordinates. If we do that, and the rest of it is very simple, we have a way of bootstrapping ourselves back to fully covariant expressions. Now, in Gaussian normal coordinates, all of those vectors are very simple. So remember that the normal vector we get by calculating the gradient of the function that describes the hypersurface. So the normal vector was defined to be proportional to the gradient of that function phi that describes the hypersurface. So if we go back to our Gaussian normal coordinates, well, we set up the coordinates in such a way that our hypersurface was a hypersurface of constant t, right? It was t equals 0. So in Gaussian normal coordinates, phi that describes the hypersurface is just t, and the condition is that t is equal to 0 on the hypersurface, which means that n alpha is going to be proportional to the gradient of phi, which means it's going to be something that has only a time entry in it. And in fact, here I don't have to worry about normalization because the metric is such that this vector is already normalized. So in Gaussian normal coordinates, we have a very simple expression for the normal vector. And here I'll use my notation equals with a star on it. The star is a reminder that this equality is only an equality in a specific coordinate system. N with the index up is also very simple. It has a time entry equal to 1, and that's it. Again, in Gaussian normal coordinates, these guys are going to be very simple because all the spatial coordinates xa agree with the ya coordinates on the hypersurface. So in those coordinate system, E alpha 1, it starts at 1, is going to be the vector with no entry along the time direction, but it's going to have a 1 entry here and 0 entries everywhere else. E alpha 2 is going to be 0, 0, 1, 0. And E alpha 3 is going to be 0, 0, 0, 1. And basically, those are all the outcomes of the partial derivatives of y with respect to y. Okay. Well, what do we do with that? Well, let's think about the extrinsic curvature. The extrinsic curvature is defined in this way, right? I'm just consulting myself here because I want to be sure. Okay, let's do it this way. The extrinsic curvature in Gaussian normal coordinates is a half the time derivative of the metric evaluated at t equals 0. The time derivative of the metric in that coordinate system is the Lie derivative of the metric along n. Let me do it differently. I'll just tell you what it is, and then we'll verify that this is it. The claim I want to make is that the covariant expression for KAB is where you take, is there a half? No, there's no half. You take the covariant derivative of your normal vector and you project it down to the hypersurface with the tangent vectors. And this I would regard to be, really the fundamental definition of the extrinsic curvature. This is completely covariant. I've symmetrized the indices here, and that will guarantee that KAB is symmetric in its two indices. All right. Well, how do I know this? All I have to do is to verify that in one coordinate system, that in the coordinate system we're familiar with, that we have agreement between this definition and this result. So then it's just a matter of simple computation. So basically the point is that this is a scalar, or this is a bunch of scalars with respect to space-time coordinate transformations. And if I evaluate a scalar in one coordinate system, well, it has to be that scalar in all coordinate systems, right? So this is a tensorial equation. In fact, it's a scalar equation. So if I evaluate the right-hand side in any coordinate system, including this one, and it agrees with the result in that coordinate system, then I know that this is a result that will agree in all coordinate systems. So that's the idea of bootstrapping ourselves. We're turning something like this into something like that, which is fully covariant. And when I evaluate the right-hand side of this, it doesn't matter which coordinate system I pick for the space-time coordinates. All of this is completely, all of this gives rise to a scalar in a bunch of scalars, a collection of scalars in with respect to those coordinate transformations. Okay, so now all we have to do is to calculate the right-hand side in Riemann normal coordinates. So the right-hand side in in Gaussian normal coordinates. Yep.
Something can be a scalar in a four-dimensional spacetime and a tensor in a three-dimensional spacetime. Can't you do a four-dimensional change of variables keeping the time component fixed and get a non-zero Jacobian? Wouldn't that same change of variables need a covariant correction term in the three-dimensional space?
Okay, let me try to clarify this. In the bulk, we're using this coordinate system, completely arbitrary coordinate system. In the hypersurface, we're using this coordinate system, completely arbitrary coordinate system, right? Now, there's going to be a relationship between those two coordinate systems, but if I can change this one without changing this one, and I can change this one without changing this one, right?
What if we did the same coordinate transformation, except in the bulk, we did the same coordinate transformation as the three-dimensional ones and kept the time fixed?
Well, so that would be in a context where I've adopted the Gaussian coordinates, and I decided to change only the YA coordinates, right? So, but this is very restricted because what I want to claim here is the freedom to have an independent change in the space-time coordinates or have an independent change in the spatial coordinates. Right? So basically what I want to have is a formalism where I have the freedom to change this independently of that. So, this reflects a choice of grid on the hypersurface, and I can keep this grid and do whatever I want with the bulk coordinates. Or I can keep the bulk coordinates alone and change my grid, and that will be, that will mean a different choice for YA. So basically here, what I want to have is the ability to have independent coordinate transformations in the bulk and in the hypersurface. So we have two sets of coordinate freedoms, and they're independent, and they're independent from each other. The first one is where we change the bulk coordinates, keeping the intrinsic coordinates unaltered. And then the second freedom is where we change the intrinsic coordinates. And in that case, we keep the bulk coordinates fixed. And the point is that I will have tensors relative to this, and I will have tensors relative to that, but they're very different things. If I only change this and not change that, those tensors will in fact be scalars relative to those coordinate transformations,
So,
and vice versa.
are you saying that you can just choose those to be scalars in the bulk?
No, I'm saying that, for example, a quantity like the induced metric, I can prove that if I change the bulk coordinates and keeping y fixed, that those indices will be such that this guy will not transform as a tensor under those types of coordinate transformations. They will all transform as scalars,
Yeah,
right?
it's
So the indices tell you what's going on. On the other hand, if I do these coordinate transformations, then all of these guys will, this guy will transform as a tensor relative to this set of coordinate transformations.
I understand.
So that's how we can have, tensors in one sense that are scalars in the other sense.
It's because the definition of the coordinates cancel out the Jacobian matrices essentially.
Yes, I'm not
Sorry, I'm
sure what that means,
those
but
E vectors, those normal vectors.
yeah. So those are, designed. Those are, their role is to basically compensate for, for the changes in this. They are compensated by these guys, and then all of this, basically becomes a collection of scalars relative to this, but a tensor relative to that. Yeah, so it's a pretty important point. So in many textbooks, the distinction is not made. So people, for example, going back to the extrinsic curvature over here, they will define the extrinsic curvature as something with space-time indices, and they'll define it in this way. And they won't do the projection. The projection will be understood. Or they'll say that the extrinsic curvature would be the pullback of this on the hypersurface. And they will not distinguish between the extrinsic curvature as a 3 tensor and the extrinsic curvature as a 4 tensor. Well, I don't really like the extrinsic curvature as a 4 tensor because, because to me it's sort of conceptually, conceptually it's not a 4 tensor. Conceptually, it's really something that belongs to the hypersurface, is defined only on the hypersurface, is completely tangent to the hypersurface, and of course I can promote it to a 4 tensor this way, but it doesn't particularly play a role. It doesn't really help me to do that. I find it's much better to be explicit with the projection operators here and make sure that what I'm defining here is really something that's defined entirely on the hypersurface as a tensor on the hypersurface, a 3 tensor, as opposed to a 4 tensor for which many components don't play a role or are not even defined or whatever. Right. Okay, so that's just a small remark. Okay, so let's just do the calculation on the right-hand side using our coordinate system. So what we have on the right-hand side is n alpha covariantly differentiated, so we just do that. And those are the 4-dimensional connections, so all of this is 4-dimensional operations. So we have a gamma, alpha, beta, and gamma. In my Gaussian coordinate system, n is a constant, so the first term doesn't give me anything. And the second term in my Gaussian coordinate system, so now I'm putting my star on it, on this to specify that I'm dealing with this particular coordinate system, and gamma only has a time entry of -1, so I kill the minus sign with nt, and then I force this index over here to be a t. Well, that's pretty much all there is to it. This is recognized now as being symmetric, so I can symmetrize the indices here, and I'm not changing anything. I can then multiply by my tangent vector, by my tangent vectors. And if I do that, well, I get my Christoffel symbol. But these guys have also very simple structures, right? So this guy over here will force alpha to be equal to A. This guy over here will force beta to be equal to B. So they're just a bunch of Kronecker deltas. So the point is that this on the right-hand side, defined covariantly, evaluates to this in my Gaussian coordinate system. And this is something we computed before, happens to be, well, the KAB quantity we had before. So this was, as I claimed before, a scalar in Gaussian normal coordinates. So what do we have at that stage? We have this scalar being equal to that scalar in a specific coordinate system. And equality among scalars is something that is, true. If it's true in one coordinate system, will be true in all coordinate systems. So this is, just to spell out the argument, these are scalars in space-time. These also are scalars, I should say space-time scalars, but anyway. And what we have is equality of scalars in Gaussian coordinates, which guarantees equality in all coordinates. And therefore, I know that this definition for the extrinsic curvature is actually a valid definition. So what I was trying to do before was to go backwards from here to there. But in my notes, I'm doing it this way, so I preferred not to confuse myself. So basically, this is the bottom line, that we can promote our coordinate-specific definitions into something covariant by just, recognizing that this is the appropriate combination of things that reproduces this in my Gaussian coordinate system. But again, we have equality of scalars in space-time that guarantees that this is a definition that will be valid in any coordinate system. And that becomes a more useful way of computing the extrinsic curvature, and we're going to see that later on today. When you want to compute this thing, it would be very inconvenient to every time have to set up a system of Gaussian coordinates around whatever hypersurface you're considering. So in practice, it's much easier to not do that, and in fact use the covariant formalism, where you're dealing with whatever coordinate system you're given for the bulk, and then you have your own coordinate system for the hypersurface, and you just figure out all the basis vectors, and then you carry out those operations, and you get your extrinsic curvature this way. So this is really the practical route to calculate it. I think that route here was more informative in terms of working out the relationships, for example, between the Riemann tensor and the extrinsic curvature. All right? Is this all clear? Okay. Well, now that we've done it for the extrinsic curvature, we can keep doing it. We can also bootstrap those expressions into covariant expressions, and again, the trick is to involve the basis that we're given over here. As it turns out, we'll be able to bootstrap this one and this one, but we won't be able to do anything with that one. And the reason is because this one involves the second-time derivative of the metric, and we don't have anything analogous to that. So by doing the embeddings and doing what we've done, we can actually calculate the extrinsic curvature and relate it to the first derivative of the metric, but we don't have the ability to do that also for the second derivative. The point is this. When I define the extrinsic curvature this way in its fundamental definition, what I recognize from this is that I need to know how to evaluate the derivative of the normal vector. But I only know the normal vector on the hypersurface itself. So the only directions that are accessible to me when I evaluate the derivative of the normal vector are the tangential directions. And the extrinsic curvature basically just measures the way that the normal vector varies, but purely on the hypersurface. It measures the rate, the gradient of the normal vector, as you move within the hypersurface. if I ask you to calculate how the normal vector varies as you move off the hypersurface, you wouldn't know what to do, because that operation is not defined. If my normal vector is defined only on the hypersurface, it's not defined off, either below or above the hypersurface, and therefore its derivative in those directions is not defined. So the extrinsic curvature captures the gradient of the normal on the hypersurface, the purely tangential gradient. To calculate this guy, and basically, if I wanted to calculate this guy, I would have to calculate an extra time derivative to everything, which means taking an extra derivative off the hypersurface. And I don't have enough information. With all the geometrical quantities that we've introduced, including k, I don't have enough information purely on the hypersurface to be able to say anything about this. In order to say anything about that, I have to know what's going on, elsewhere, above and below the hypersurface. Yep.
Will this mean that there's no covariance expression for the region?
Yep. Some components you can capture, and you can see it from the Einstein tensor itself, right? I'll be able to bootstrap this one. I'll be able to bootstrap this one, no problem, because all of those are defined purely in terms of geometric quantities on the hypersurface. But the other components of the Einstein tensor involve this and that I cannot capture by just looking at what's going on purely on the hypersurface. So that's why I'll write down covariant expressions for these two and these two, but I won't say anything about the other ones. But that turns out to be important on physical grounds when we start talking about the breakdown between solving the, so splitting up the Einstein field equations in terms of constraint equations that you have to solve on a hypersurface to set up the initial values, and doing time evolutions away from that hypersurface. So I'll come back to that, and that's something I'll talk about this afternoon. So right now I'm running out of time, so I'll just write down those expressions I promised you. Let's do it here. Well, it's pretty easy to do. I need a covariant expression that represents the left-hand side here and the left-hand side there. So I'll just write it down. I think you'll recognize it right away. So for example, this guy over here, I can express as because that quantity in Riemann normal coordinates happens to be equal to this over here. So I've already claimed without proof that while the right-hand side is a space-time scalar, right? It's a bunch of space-time scalars. The left-hand side has to be also a bunch of space-time scalars. Sorry. Yeah. And this, projection of the Riemann tensor, relative to all my basis vectors, clearly that gives me a whole bunch of scalars. Contraction with n in Riemann in Gaussian coordinates gives me a t for a mu. Contraction with all the spatial basis vectors force alpha, beta, and gamma to be a, b, c. So basically, in Gaussian coordinates, those scalars happen to be equal to those components right here. And therefore, they happen to be equal to the right-hand side. So this perfectly covariant expression on the left-hand side will turn out to be equal to this perfectly covariant expression on the right-hand side. KAC. And same thing for the second one. So the purely spatial components of my Riemann tensor I can get by just projecting with all my tangent vectors. And the right-hand side for that is the intrinsic curvature plus all the extrinsic pieces. So manifestly covariant on the left-hand side, manifestly covariant on the right-hand side. We also have, all the right properties. So with respect to space-time coordinate transformations, everything on the left-hand side is a bunch of scalars. Everything on the right-hand side is a bunch of scalars. Relative to three-dimensional coordinate transformations, purely intrinsic to the hypersurface, we have a tensorial quantity on the right-hand side, and we also have a tensorial quantity on the left-hand side. So the tensorial nature is the same on each side, in whatever point of view you take on the tensorial nature of this, whether it's a space-time or a hypersurface perspective. This component of the Einstein tensor is the normal component. And that turns out to be equal to a half the three-dimensional Ricci scalar minus the squared quantities. And finally, these guys over here are the mixed normal tangential components. And that's equal to dBk BA minus DAK. And again, those are all the components that we can capture this way. The other guys, because of these terms and the second derivative terms, those cannot be captured in terms of geometrical information purely on a hypersurface. You have to know how things, evolve away from the hypersurface in order to capture these things. So these are the Gauss-Cadazzi equations in covariant form. And those would be the contracted Gauss-Cadazzi equations. And those are interesting because, again, we'll come back to that this afternoon. Those give me, part of the Einstein tensor. Therefore, we have access to part of the Einstein field equations in those equations. And we'll think a little bit more about that later in the afternoon. Let me just see if I have anything more to say on this topic. I don't think so. So any questions before we break?
You may have said it, but are those second-time derivatives a feature of any coordinate system you can construct?
Sorry, say again.
Are the second-time derivatives that appear in the Einstein tensor and the Riemann tensor a feature of any coordinate system which you could construct with the x axis or a hypersurface coordinate?
Okay, I'm not sure I'm getting your question. So you're asking whether I can...
So could you construct a coordinate system, hypersurface coordinate system, where those second derivatives
don't appear?
Yeah.
Oh, no, I don't think so. I don't think so. I think if you had that, I think you would have a very singular type of coordinate system where something would, something really funny would happen with those curves. I mean, they would either stop it in one direction or something like that. I mean, I think it would be So I think the answer is no. You couldn't do that unless you had a pathological coordinate system in some way. Yeah. Yep.
There's another way of saying that the fact that you can't write everything in the covariant form is like saying that that sigma doesn't have its own Einstein equations that it satisfies. So it doesn't. There's not a. You can't just take a slice of space-time and then develop that using the Einstein equations.
No, that's right. So you're certainly missing. You're missing information about the cross derivatives on the hypersurface. So those second derivatives, you would always miss that information. So you can capture part of the Einstein tensor, but not all of it. So that's exactly the point.
But how did people then justify the brain world theory where they say we're on some high dimensional space, or a slice of high dimensional space, because then shouldn't our universe not satisfy the Einstein equation?
No, so that's still fine. So the point is that here we're asking a very specific question. So, and the specific question is, how can we capture by looking at things entirely defined on the hypersurface, how can we capture information about the ambient curvature, right? So that's a specific question. And the requirement is that we only use information on the hypersurface to do that, and then the conclusion is that we can capture something, but not everything else. In brain world type scenarios or anything that involves hypersurfaces, even in GR, you don't have to say, I only want information on the hypersurface. You can say, well, in principle, I can evolve things away from the hypersurface. I have a theory that tells me how things evolve away from the hypersurface. So I do have a means to calculate these things in a brain world scenario. I mean, I have a theory that describes the bulk, and I have the theory that describes the hypersurface. But the point is that I have access to information elsewhere. If I said that I didn't want, so if I wanted a theory that only is based on information purely accessible to the hypersurface, then I couldn't do it. So then there would be no such well-posed theory that would tell me what's going on in the bulk. I need more information to have access to the bulk, and that's what we're saying here. Yep.
So if the normal vector is a killing vector, then it simply extrinsic curvature vanishes. So
Yep.
So then is there anything special about the surface in that case?
Yep. I'll talk about that this afternoon. So that surface would be a moment of time symmetry. So if it vanishes only once, so if you have a whole stack of surfaces and KB vanishes on one of them, and then that surface by definition describes a moment of time symmetry in the evolution of your space-time. If you have a whole stack of surfaces and KB is zero everywhere, then you're right. The normal vector is a time-like killing vector, and in that case, well, you foliated your space-time in terms of the hypersurfaces that are orthogonal to your killing vector, and those have that property of having a vanishing extrinsic curvature. I'll say more about that this afternoon. So before you break, I can return the homework from last week.